Today we're diving into a paper that explores a novel approach to training language models. Think before you speak. Training language models with pause tokens proposes a method to improve model performance by introducing delays in the token generation process. What's the core idea behind this approach?
The paper challenges the traditional way language models generate tokens, where the next token is produced immediately based on the preceding ones. They propose introducing a pause token that essentially forces the model to pause and process more information before committing to the next token. This pause allows the model to consider a wider context and potentially make more informed decisions.
That's an interesting concept. How is this pause token implemented during training and inference?
The pause token is a special character that's added to the input sequence. During pre-training, these pause tokens are inserted randomly into the training data, forcing the model to learn to handle delays. During fine-tuning and inference, the pause tokens are appended to the input, delaying the model's output until the last pause token is encountered.
So the model is essentially learning to think before it speaks. What are the potential benefits of this approach?
The authors hypothesize that the pause token allows the model to explore a wider computational pathway, potentially leading to more accurate and nuanced responses. They argue that this approach can be particularly beneficial for tasks that require reasoning, understanding, and long-term context recall.
That's a compelling argument. What are the key findings of the paper?
The paper demonstrates that training models with pause tokens during both pre-training and fine-tuning leads to significant performance improvements on a variety of downstream tasks. They observed gains in tasks like question answering, reasoning, and general understanding.
That's impressive. Can you elaborate on these specific gains observed in the experiments?
For example, on the squad question answering task, the pause-trained model achieved an 18% improvement in exact match score compared to the standard model. They also observed gains of up to 8% on the common sense QA task and 1% accuracy improvement on the GSM-8K reasoning task.
Those are substantial gains. Did the paper explore any variations in the number of pause tokens used?
Yes, the paper investigated the impact of varying the number of pause tokens during fine-tuning and inference. They found that there's an optimal number of pause tokens for each task, beyond which performance starts to degrade.
That makes sense. It seems like there's a sweet spot for the amount of thinking the model needs to do. Did the paper also explore the robustness of the pause-trained models to variations in the number of pause tokens during inference?
Yes. They tested the model's performance when the number of pause tokens during inference differed from the number used during fine-tuning. They found that the pause-trained models exhibited a graceful degradation in performance, even when the number of pause tokens was halved during inference.
It's encouraging. It suggests that the models are somewhat robust to variations in the computational delay. Did the paper compare the performance of pause-trained models with models that were simply delayed using filler characters like periods?
Yes, they did. They found that using filler characters as pause tokens did not lead to any performance improvements, suggesting that the model needs to be specifically trained to utilize the pause tokens effectively.
That's an important distinction. It seems like the pause token is more than just a placeholder. It's a signal that the model learns to interpret. Can you elaborate on the theoretical insights provided by the paper?
The paper provides a theoretical framework to understand why pause tokens can be beneficial. They argue that pause tokens effectively increase the computational width of the model, allowing it to explore a wider range of operations and potentially represent more complex functions.
That's a fascinating perspective. Can you explain how pause tokens increase the computational width?
In a standard transformer, the number of operations performed in parallel is limited by the number of input tokens. Pause tokens effectively increase the number of parallel operations by extending the input sequence length. This allows the model to explore a wider range of computational pathways and potentially learn more complex relationships between tokens.
So pause tokens essentially provide a more efficient way to increase the model's computational capacity without significantly increasing the number of parameters. Did the paper discuss any limitations of this approach?
Yes, the paper acknowledges that pause training requires additional computational resources during pre-training, which can be a barrier to wider adoption. They also note that the optimal number of pause tokens may vary depending on the task, and that further research is needed to understand how to make pause-trained models more robust to variations in the number of pause tokens during inference.
Those are important considerations. Can you summarize the key contributions of this paper?
The paper introduces a novel approach to training language models by incorporating pause tokens, which effectively delays the token generation process. They demonstrate that this approach can lead to significant performance improvements on a variety of downstream tasks, particularly those that require reasoning and understanding. The paper also provides theoretical insights into why pause tokens can be beneficial and highlights the need for further research to address the limitations of this approach.
This was a very insightful discussion on the technical aspects of this paper. Thank you for sharing your expertise.